Okay, guys, let's look at these. How do we do?
First one.
We're doing the first one. Any questions about the first one? Base takes the most acidic H, and then the anion does good old SN2. Make the anion, we enolate, stabilized, and we do the old SN2. We could have did that reaction in organic 1. There we go. Questions? This is ultimately haloform reaction. This is going to put 3 bromines on here, right? Exhaustively brominate. There's no H over here to remove, so we can't make anion over here. Then the hydroxide is going to come in, right? And electrons up, back down, kick that off, and so we actually get that plus the CBr3 leaving group, right? But this is not the end of the reaction. This takes the H because that's acidic. This is a pretty strong base. That's the end of the reaction. You get O minus. To put the H back on the O minus, you got to have H plus workup. So that's actually where the H comes from. It's ultimately a haloform reaction. Turn the methyl ketone into a carboxylic acid, right? Down here, this is just thermal decarboxylation. The carboxyl group with the carbonyl beta is going to be decarboxylated. This loose CO2, the H ultimately ends up here. How do we do on those? The mechanism is pretty much an aldol followed by a Michael.
Oh, you do that first?
You could do it the other way. You could do an imine followed by a sort of a Michael. I did aldol base. Typically acid-base reactions faster. Base takes the acidic H. The anion then attacks carbonyl, electrons onto oxygen. So we made this bond here. Carbanion attack carbonyl, electrons onto oxygen. There's a methyl on the carbonyl. This can pick up an H from solvent. But then I realized that ultimately I'm going to remake anion here. So instead of taking an H from solvent, I let it take an H from this guy. Because that H is going to be somewhat acidic. So I just did proton transfer to give anion here. Basically the proton moved to the oxygen, now we got anion here. Now we can come in here and kick that off and make our alpha beta unsaturated carbonyl compound. But now this is like an alpha beta unsaturated carbonyl compound. We got this nucleophile. You can add beta, and that's how we get the 6-membered ring. Like a Michael addition to give this. This can just do a proton transfer. The H plus can be moved to the anion, leave the lone pair here. H plus transfer gives a product. You could have did this the other way. You could have the amine attack carbonyl first, and with the amine attack carbonyl, you could get something like this, where this is the amine. Okay, nitrogen replaced the carbonyl oxygen. You could have then made anion here, and then this could have then came in here and done this. Because this is like a carbonyl. I mean, if we had, it's a polarized double bond. It's imine. We can attack carbonyl electrons onto O. We can attack carbon electrons onto N. That would give nitrogen anion. It would then need to pick up a proton from like methanol. Actually, in this reaction, you may need acid workup. This may not be catalyst because at the end, you still have an acidic proton. Actuality, that may consume all of your base, and at the end, this may actually be anion there, and the only way to put proton on is to add in some acid, where methanol is not going to be strong enough to protonate that. That could be the case there. How do we do on that mechanism? Combination of aldol followed by Michael.
So you took an H from the acidic carbon and used that for the H plus transfer? You said that you could have used methanol. Like, do you have to do that?
Have to do what?
Like when you took the H from the acidic carbon, or you took H from the carbon where the cyanide was on it, and put the anion there. Do you have to do that, or can you just make the O with the methanol with the
You could, but then you got to make anion here. So the methoxide would just come back and make anion there. We can just do that. Question, guys. Question, guys. Where's this going to take a proton from? We got methanol. What's the pK of methanol?
Like
Same as water.
16.
About 16. What's the pK of that H that's remaining right there between the two withdrawing groups?
Lower than that.
That's about 10 to 12. Which one's more acidic? That one. So where's this more likely to take a proton from? And if we just take a proton internally, we've always called that sort of H plus transfer. So that's actually the more appropriate place to take it from. More acidic.
If you had taken it from methanol and then used MEO to form the anion there, would that have been acceptable?
It would have been okay. Then you can just take the resulting anion and take the H.
Yeah.
You're just doing multiple steps when you could have just did it internally, and internally we call it proton transfer.
I got you.
On the bottom is hopefully pretty easy. Be the aldehyde. Okay, just to give you some chance to see where you're at. Test on Friday, right? What did we begin with? Simple additions, hydrates, cyanohydrins, acetals, imines, enamines, half acetals, that type of stuff. With the imines, we have a lot of applications of that. Hydrozones, oxenes, Wolff-Kishner, Strecker amino acid synthesis, a variety of things there. Wittig reaction, then we moved into alpha carbonyl reaction, aldols, tautomers, alpha halogenation. Then we did like direct alkylation, LDA, and then we did indirect or something like number 1 here, where we can use a weaker base using a more acidic starting material. Aldol reactions, and we did like Claisen, Diekmann. Then we got into Michael reactions, adding nucleophiles beta. Then we ended up with we did a Robinson annulation. That was an aldol followed by, no, that was a Michael followed by an aldol.
Formed a ring.
Yeah, we formed a ring in this mechanism here. That was like an aldol followed by a Michael. Or you could have did it sort of the another way. That really doesn't have a name. The Robinson annulation kind of got a name because it was pretty prominent. Okay, a variety of miscellaneous things today. Let's see what type of questions we have. Let's look at some of the miscellaneous things in the white handout, the one you printed. Synthesis of Vioxx. We'll post this upstairs. Vioxx used to be $1 billion selling drug to treat things like arthritis. It had to be pulled because of heart side effects, heart-related side effects. Everybody with me? Okay. Here's a synthesis of Vioxx. First off, here's Vioxx here. It's been pulled for about 15 years now. Look at this. Pretty simple organic molecule, yeah? $1 billion, right? Okay. Here's a synthesis of biotics starting with the sulfur compound, yeah? If that sulfur was an oxygen, that would be like an O-methyl coming off the benzene ring. What would be the name of that compound? O-methyl. Anisole. Anisole. And the sulfur, we can call it thioanisole. Okay? So begin there. You know, you might say, well, how is this made? Well, ultimately, everything's made from what? Pearl. MacGyver used to make it from like carbon and paper clips. But ultimately, you tend to start with something that you can buy. That had to be made most likely, but okay, we can start there. First, most of this chemistry we've covered. First reaction is Friedel-Crafts acylation. Final exam is what? Less than 2 weeks? The sulfur, what type of director is that sulfur? Got a lone pair, and it's not a halogen. Ortho pair director. We show a pair product. There may have also been some ortho acylation. Pair tends to be preferred, less steric, especially from Friedel-Crafts. We get that ketone. We've never seen oxidation of sulfur like that, but you can oxidize sulfur. That's an SO2. It's called a sulfone. What's next, though? Top right. What's going on there? Alpha bromination, using bromine and acetic acid, right? Yep. Why in the world would they want to put a bromine on there? So they can come in and then take it off. And when they take it off, they're not taking it off with an H. If you replace it with an H, you go back here. But with the leaving group, you have some chemistry you can do. You cannot replace an H with something, but you can replace a bromine by substitution. Okay? And so they come in here with this carboxylate anion. And this comes in here, boom, kicks off the bromine, and we make that bond right there. Used to be bromine, now good old SN2. From there, we're just one step away. It's just an aldol condensation. Now, aldols typically you might use like hydroxide or methoxide, but you can use a neutral nitrogen base. Triethylamine, yeah. It is basic enough to do an aldol. Okay, means tend to be slightly basic. But where are we making anion? How is it cyclizing? We're obviously making a 5-membered ring here, yeah? What anion is attacking what? Could you break this apart? Aldol gives alpha beta saturated carbonyl, alpha beta saturated carbonyl. Here's the alkene that the aldol gives, right? Everybody, aldol gives an alkene, right? You all know that, right? I mean, that was clarified after day 1, right? Good. Which carbon of the alkene was originally the enolate? Top or bottom? The top, because the enolate would be next to a carbonyl. Which carbon of the alkene is next to a carbonyl? The top. All right? Yeah. Okay. Top was the enolate. The bottom thus was originally what? Carbonyl, right. Okay. Break that apart into enolate and carbonyl. You see the enolate and carbonyl? Where's the enolate over there? It's between the phenyl with no group on it, CH2 carbonyl. Right here. This was the enolate. Okay, it's not a ketone, it's actually the enolate of an ester. And what does it attack? Well, the carbonyl. The carbonyl was bonded to the ring with the thing on it. There it is. It just attacks here and off you go. And when you lose water, you're going to get that. Please be able to recognize an aldol reaction, how it came to that point. Okay? Now, you might say, well, we could have perhaps made anion there, but what would it have attacked? You can't really attack anything to make a ring. I mean, it could make that'd be a 3-membered ring, and that would not be an aldol, because that's an ester. You'd kick that off. Okay? So please recognize that. You lose water in this reaction, and there you go. You got a $1 billion drug called Vioxx, or it used to be until somebody. heart problems, and then let's look at what else is in here. Toxicity of Tylenol. Tylenol is toxic. You get above 100 milligrams per kilogram, it's going to be bad for your liver. Okay? Everybody know how much you weigh in kilograms? Okay.
I like to tell myself
Weigh a little bit more than that.
Sounds like a sixth grade. I know.
Okay.
In sixth grade, I was the same weight that I was in.
If you weigh 50 kilograms,
Oh my God.
that's probably like a small person. 100 milligram per kilogram, 50 times 100. What is that, 5,000?
Yeah.
Okay, 5,000 milligrams, how many grams is that? 5 grams. So 5 grams of Tylenol would be toxic. How many extra strength Tylenol is 5 grams?
A lot. 5, 10.
10, because they usually have half.
About 400.
So for a small kid, 10 tablets is going to be toxic to the liver, okay? So that's how you do your 100, milligram per kilogram. That's usually how dosages are done, yeah? Okay? Now that's a lot, but a kid could eat them like peanuts and then, you have a problem.
Why does alcohol have a synergistic effect with Tylenol?
Synergistically bad effect.
Yeah.
Because the Tylenol toxicity is to the liver. Well, if the liver's busy metabolizing the alcohol, it can be kind of overloaded.
Okay.
That's a very generic answer, but the toxicity is to the liver, yeah. Okay. Now, just because 10 extra strength Tylenol is toxic to that person, does that mean that 9 is not?
No.
Okay, we've got sort of a line, but that doesn't mean that, this right over here is not toxic either. It's all kind of, all right. There's usually some statement. That doesn't mean that maybe 80 milligrams per kilogram is not a little toxic. Typically, the dosage in hospital is like the doctor will say, well, let's give 20 milligram per kilogram. Okay? Then the person has to do some calculations. Okay, Tylenol is toxic to the liver. Why? Well, here's Tylenol. It's not necessarily toxic, but Tylenol gets metabolized to this structure here. It's a metabolite. It's an oxidative metabolite. Usually your body oxidizes things. But look at it. What do we have here? It's an alpha-beta-saturated carbonyl compound now. And these do tend to be quite reactive at the beta position. The microreaction, okay, even more so than just carbonyls. And then the proteins in your liver, particularly, which often have amino groups, start adding Michael addition to this. And we make this covalent bond between the protein, the beta carbon of the alpha-beta and carbonyl system. Now you've modified your proteins and basically ruined them, unless they can eliminate back off. Now that could theoretically eliminate back off, but it tends to be slow. Okay. So it's actually the metabolite that's toxic. That's the same thing with alcohol. When you drink alcohol, it's not really ethanol that's giving the effects. In your body, the ethanol is converted to this. It's an oxidation, right? In class, we did it with one of the big three. Of course, it doesn't stop the aldehyde with the big three. It keeps on, right? But in the body, this happens as acetaldehyde. And that's what really leads to the effects of ethanol. A lot of times, metabolites can have the effect. On the other hand, sometimes metabolites may be completely inactive, and all the effect is coming from the original. Okay, you ever heard of glutathione? Glutathione protects us from things like that toxic metabolite, to a degree. So glutathione is a peptide that has an SH on the end, residue. Like like a cysteine amino acid. And this is a good nucleophile, and it adds. Okay? Problem is, this is glutathione's purpose. And if it adds, it keeps the your proteins from acting. So it's a sacrificial nucleophile that your body uses. It serves a purpose. And it gets rid of all this by this. Okay? Hey, let me react here. Liver proteins, you don't react. Let me react. Sulfur's a good nucleophile. Your body uses sulfur a good bit as nucleophiles. Problem is, glutathione is limited in your body. And you could run out. And so if you have too much of this, you just run out, and then your liver starts reacting more and more. Because your glutathione gets depleted. Actually, if you overdose on Tylenol and go to the hospital, they will give you something. Anybody know nursing? Anybody in? What do they give you if you overdose on like Tylenol? It's called Mucomist. I believe. Okay. Mucomist is very similar to this right here. They give you an SH compound. So it can get in there and react with this, and so your proteins won't react. So it's like an antidote. Your body has some too. And once this thing gets excreted, because this peptide tends to be polar, and this can be excreted out, and you've removed the toxic metabolite. Chemistry of superglue. Superglue is this here. It's the methyl ester of cyanoacrylate. Superglue is a liquid, but it will quickly, anybody used superglue before?
Yes.
Liquid, it comes out, what does it quickly do?
Dry.
Solidifies.
I don't like it. It gets all on your hand and stuff.
I used to work at the Poison Center when I was in graduate school. And someone called in and they had super glue. They thought it was lip stuff.
Solid. Cat lips forever.
I don't know if they were talking, if they were just playing with me or what, but I vaguely remember something like this. Reached into my purse, the person said, and
Why do you have super glue in your purse in the first place?
You never know.
maybe I just dreamed this one night.
I hope so.
Okay, so why does the superglue liquid, why does it turn into solid? Is it just drying? No, it's not just drying. It's a polymerization reaction. Okay, here we go. It's initiated by an anion or nucleophile. And the anion adds microaddition. Oh look, this is an alpha beta unsaturated carbonyl. It's also alpha beta unsaturated cyano. Very reactive. Because the resulting anion is very stable. Not only stabilized by the carbonyl, but also by the cyano group. So this addition is very stabilized. We can put anion onto nitrogen by resonance or oxygen by resonance. Now in class, we just typically picked up a proton and said that's it. How can this polymerize? Well, right here, instead of this picking up a proton, it can add again. This anion can do a microaddition. And that would give that bond, and then electrons here, this anion. Well, what can it do? It can add again. You just keep on adding and adding, and boom. Of course, in chemistry life, this happens like that a billion times. And once you get this huge polymer, it's now a solid.
Where did the catalyst come from?
Good. Where does the catalyst come from? Right there. If I put super glue right there, what's it going to do? It's going to boom, do its thing. There's traces of base everywhere. On your fingers, your lips. There's traces of base here. All it takes is a trace. It's everywhere. It's everywhere. Traces of bases are okay. I don't think you can find any surface or anything that is not like 100% absolutely neutral and Okay, good question. Yeah. Okay, this is called an anionic polymerization because it's initiated by an anion. There's your anion. Okay, question?
How come in the super glue bottle it doesn't just like
Ah.
Okay, apparently there's
Smart
no,
guy.
there's in there. Okay, somebody asked that a long time ago. They were like, well, how do they get it in there? Because I mean, why doesn't it just, yeah.
They created it.
I'm sure there's some production technology there that goes into this. But I'm sure along the way, since superglue was invented, whatever, 50 years ago, at some plant, they probably had a problem. They had a big tank of liquid and it all just, it all just turned to solid because somebody messed up and they got exposed to a little bit. Okay? They were transferred and all the lines just solidified because of some exposure to the atmosphere or something. Okay? But yeah. Can anybody, does anybody think you can take some super glue out and it not do that?
No.
Yeah. If you can, videotape it and let's okay? It's going to polymerize. But here's the chemistry. Do you understand the chemistry? Instead of it picking up a proton, if you just keep doing this. Actually in lab, whenever you do micro additions, they're always prone to polymerizing. Because you're like, I just wanted to add, I want you to pick up a proton. And that'll be it, just this monomer. Well, it may not listen to you, so you have to do things just right. But that's super glue.
If you put it in acid,
Yeah, that's what I thought saying. Yeah, if you just expose it to a ton.
You're asking research questions. I don't know. You know.
Time to cut this out.
8-week lab on super.
Okay.
That would be cool.
By the way, this almost should have been on some nomenclature, but that right there, anybody know the name of it? That's acrylic acid. Okay? And when you start making esters of acrylic acid like that, that's called methyl acrylate. Okay? You put a cyano here, that's called methyl cyanoacrylate, which is what we got up there. You see it? You see the name? Acrylates. Okay? A cationic polymerization is initiated by a cation, like H+. You can also have radical polymerizations that are initiated by radicals. There you have to generate a radical somehow, and then it begins the process. So, that's an anionic polymerization. Okay, acrylates. Where have you heard acrylate before? Acrylic.
Yeah.
Why do you know acrylics?
Acrylic paint.
Acrylic paint, yeah. 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 What would you call this material?
Plastic.
Plastic is a very general term because this is also plastic.
That's why you grab the load.
But what are these plastics? What are types of plastics?
Polymers.
Specific names. Names.
Acrylic.
Polyester, that's more like your shirt. Okay.
Polyethylene.
Usually polyesters are not plastics, although they could. Any others? Polystyrene, typically styrofoam, that tends to be not really a plastic. If you blow air through it, it makes styrofoam.
Is that polyacrylic? Is that what it is?
Well, we're going to get there. Acrylic type polymers. Others can be like polyethylene, like trash bags. These tend to be thin. Polypropylene. This is probably polypropylene. PPE. Those tend to be thinner. Okay. Thick plastics. I wish I could have brought down the hoods. Your chemistry hood upstairs. It's kind of more thicker. Okay. These things tend to be more acrylics. Come from acrylates. I think and a name. I think this. I'm not sure. This could. You also have things called like polycarbonates, which some like sunglasses are made out of. They can be a little thicker. This I don't know. This could be polycarbonate. The name I'm looking for though is plexiglass. Plexiglass tends to be acrylics, and acrylics Let's look at that. So, somewhat similar to super glue, except instead of a cyano, if this was a cyano, that would be super glue. But with the methyl there, that's called methyl. Well, first off, with the methyl there, it's called methacrylate. They sort of blend in the methyl with methacrylate. Methyl here, methyl methacrylate. If you polymerize this, first off, can you show the polymer? Okay? Okay, can you show the polymer unit? This here. Well, if you polymerize this, this is the polymer unit, and it's called plexiglass or acrylic, or a more trade name, lucite. Okay? And that's something more like this. Tend to be thicker plastics. Also, the thicker you get, the less you can see through it. But acrylics, you typically can see through them well. That's one of its benefits. Okay? So you can have something real thick and still be able to see through it. And a lot of times it's like glass. It lets you see through glass. That's where the name like plexiglass came from. Where other polymers, if they get thick, they tend to be not transparent. They tend to become hazier. So that's one of its benefits. Some things down here I just pulled off of the web. This is a piano with all this plastic on it, but it tends to be acrylic or plexiglass. Here's a car that's made it thicker. This is a cube of the stuff. Inside of the cube is a liquid vial of bromine, but they put the plexiglass around it, and so it's trapped, and it's just used for demo. It's kind of cool to have that liquid in there trapped. You see it's kind of thicker. This stuff tends to be this acrylate. By the way, what is PMMA? Polymethyl methacrylate. Polymer. We call it different names. Here's an interesting application that takes us back to the beginning of Organic 1 a little bit. Physical properties. Contact lenses. Contact lenses can be made of this stuff. Okay? Problem is, this is it'd be a hard contact lens. In modern day, we have more softer. Anybody wear contact lenses? Okay, softer, yeah. The softer ones are made of more of a softer plastic, and not the PMMA, the polymethyl methacrylate. Okay. All right. The softer ones tend to be made. They're also known as sort of hydrogel. And what it is, it's a plastic that will absorb a lot of water. And once it takes on the water, it becomes a little softer, and it can bend much more easily. Well, look at this. It's actually a very similar polymer. The only difference is, instead of this being an O-methyl coming off, this is the same. It's just the ester part. Instead of O-methyl, they have OCH2CH2OH coming off. It's still an acrylate polymer. But with this OH coming off a billion times, every unit has the OH, the polymer is going to be more prone to liking water. Because water can hydrogen bond here. This polymer is going to be more what? More hydrophilic. Because of the hydrogen bonding potential there. And it's so hydrophilic that it will absorb a lot of water. Okay, there's probably some technology going into exactly how this is created. But it takes on, a lot of these absorb tons of water, and instead of it being a hard plastic, the result is a more flexible, fluidy plastic. Soft contact lens. Also, something like this is also used in diapers. Okay? Because you sometimes want to absorb a lot of water. Okay? And so they put in a material that will. So you think about that. Now, if you didn't want to absorb water, which polymer would you prefer?
Top.
The one without the hydrophilic OH group. For example, maybe you wanted to have a rain jacket that repelled water. You wouldn't want to use this, you'll absorb the water. Okay? So that takes us back to physical properties, right? And it's amazing that even though this is a bulk material, that is like, well, how does the water get there? Well, That's the fascination. How does this bulk material absorb the water? It boils down to the molecules, and to me, it's like, well, where are the molecules at? But it's there. That's the chemistry we can't see, right? But its physical properties, everything is based on structure, including drugs. Very important. Okay, where can we finish up here? Where can we finish up here? You can look up some of those things on the wiki. Any questions? Test on Friday. We went over it, basic format. There will be comprehensive spec. There's plenty of those in the workbook. Test will be returned on Monday. Everything goes well. Okay, as we will say this afternoon for the third group in lab, we'll meet down here. Final exam is less than 2 weeks. We will have a final exam review on not this Saturday at 9, but the following Saturday at 9 a.m. in this room, hopefully. We'll talk about that. I think that's it. Any last questions today, guys? See some of you this afternoon.